Alright, welcome back. So today we are going to be touching up on our naming of alkenes, alkynes, and alkynes and their cyclic forms. So we are going to start with recognizing what an alkene and alkyne is. So first of all, our alkenes. Notice how the ending there, that suffix, that ene, indicates the double bond. So that's what you're going to be looking for, is a carbon-to-carbon double bond. Now, you can get multiple double bonds inside of an organic molecule. We won't be dealing with it here, where you're only going to see just one double bond inside of our longest carbon chain. Now, you'll notice the general formula is CnH2n. So this is similar, actually it's the exact same formula as our cyclic alkanes. So you can tell that these are going to be isomers of each other. Now, of course, with these here, our example, we're just going to look at propene, getting the chemical formula and how it looks. So obviously, with this right here, so we have our prop, right? So 3 carbons. And we see that ene indicating that we need to have a double bond. So first, let's figure out what the empirical formula look like. So we got CnH2n, so we go C3H 2 times 3, so C3H6. And how this will look, so we have 3 carbons like this. Now for a double bond, we stick a double bond in, just like that. Now we can stick it anywhere. I'm sticking with smaller molecules because we're going to learn how to name the bigger ones eventually. Now we need to fill the rest in with hydrogen. So this N carbon right here, we already have 2 bonds from the double bond, so that means it can only have a maximum of 2 hydrogens, right? So now it has 4 bonds in 4 is the maximum bonding capacity for our carbon. The one here in the middle, we can see that has 1, 2, 3 bonds, so it can only take 1 bond from hydrogen, or it can only take 1 hydrogen to complete 4. And the N carbon here needs 3 hydrogens to max out its bonding capacity. Now for our alkynes, we're going to see a triple bond. So Yne signifies a triple bond, and the general formula is CnH2n minus 2. So if we did our propyne, right, so just pay attention to the ending, the Yne, prop is still 3 carbons, but what we have is our C, that's not a C. So our general formula, let's figure it out for our propyne. So you got C3H 2 times 3 minus 2. All right, so we simplify this. So C3H6 minus 2, or C3H4 is our empirical formula for propyne. Now for drawing it, right, so just like before, we're going to start with prop, so our 3 carbons. Now because that Yne, we need to have a triple bond, just like this, and of course we fill the rest in with hydrogen. So this N carbon has 3 bonds already from the triple bond, so it can only take 1 hydrogen to max out at 4. This middle carbon right here already has 4 bonds, right? So it's got 3 from this triple bond and 1 from this single bond. 4, it is maxed out. And finally, this N carbon only had 1 bond, so it needs 3 hydrogens to max out at 4. Now, this diploma example, I'll let you guys kind of do this on your own. This is just kind of alkane old diploma example here. It was supposed to be on the previous page. It's just the formatting I messed up when I made the booklet. Sorry. So just go over to the next one. So what we have right here is with these double and triple bonds, these are given a very specific name. It's called unsaturated hydrocarbons. And the definition is just an organic compound containing or a double or a triple. Keyword here is carbon-to-carbon bond. So you need to see that double bond in between 2 carbons or that triple bond in between 2 carbons. Now there is a diagnostic test that you can do the test for this. And that is you react either potassium permanganate or bromine. So if you dump a little bit of this in there, you're going to get a fast, noticeable color change. Alkanes do not have this fast, noticeable color change. Alkanes can produce a color change, which we'll get into now in a minute, but it is not fast. Keyword. Now, we have this test, right? It's a diagnostic test, just like litmus is a diagnostic test for acids and bases. This is just one for our unsaturated compounds because they only change when there is a carbon double or triple bond. Now, what you're looking for is something like this. So this is a carbon to carbon. I'm not going to spell out carbon twice. Let's go just C to C. double bond. So this molecule right here will give a positive test to the diagnostic test. Now this one right here, notice how this is a carbon to oxygen double bond. So this one will give a negative test on the diagnostic test. All right, and that's what this little paragraph down here explains. So a bromine test will be negative for propane because it's fully saturated, and positive for propene because it's unsaturated, where the double bond is carbon to carbon. Now it will also test negative for propanoic acid, which is this one right here, where the double bond is between carbon and oxygen and not carbon to carbon. All right. Now, as it mentioned right here, a negative bromine test with a saturated organic compound does not mean that there is no reaction with bromine, because we will learn later, and it's only for bromine, not potassium permanganate. So it means that all that means is that there's no immediate or fast reaction between the saturated compound. We can get a slow substitution reaction in the presence of UV light, but when we get over substitution reactions, it'll be a little more clear, but these are very slow, so you're looking for a fast, immediate reaction. All right, so that's just a little bit on the saturation stuff. Now, for nomenclature, for these right here, for nomenclature of our alkenes and alkynes, they are named exactly like the alkanes, except there's a few additional points that we need to consider. All right, so most of these additional points is that we need to have our multiple bond, our parent chain, so our longest continuous carbon chain must contain the multiple bond. So that means we cannot have the multiple bond, sorry for that noise, it cannot be in a branch, all right? So must contain the multiple bond. Now, when numbering our carbons, the parent chain is, when we're numbering our carbons in our parent chain, more importance is given to the location of the multiple bond. So in our alkanes, it was carbon 1 was close to our first branch. Now it needs to be closest to our multiple bond. So we're going to start numbering from that end. All right, and of course we need to identify where this multiple bond is. So we are going to place a number in between the root and the suffix of our name. All right, so I'll just kind of give you an example, 2 isomers of butene. All right, so we can have butene multiple bond here or multiple bond here. All right, now if we follow our rules, we start numbering the carbon closest to the end with the multiple bond. So that means carbon 1, carbon 2, carbon 3, and carbon 4. Now we will notice here in our first one, so the one farthest to the left, that the multiple bond starts on carbon 1. So therefore, the root is but. Remember, root is our longest carbon chain, and our suffix is E and E, right? Because that tells us that there is a double bond. So this is the root, and this is the suffix. Now we need to stick a number locating the position in between the root and the suffix, just like this. So we turn it into but-1-ene. Whereas the second one, we'll notice that I need to label my carbons like this, 1, 2, 3, 4. Now, just like before, I got my root, I got my suffix, but I need to put the location of the multiple bond in between them. So now we can tell that the multiple bond is starting on carbon 2, so this turns into but-2-ene. Now for our cyclic formulas, this is going to be the formula for our cycloalkene, and this is our cycloalkyne formula. So just like I showed you before when implementing the formulas, remember, N is the number of carbons when we put it in there, so these will go in just like before. So cycloalkene has the same formula as an alkyne, and cycloalkyne has their own formula. Now, as for the naming, just like the cyclic alkanes, we will need to indicate it's cyclic by putting cyclo in front. Now, when we did our cyclic alkanes, carbon 1 started on a branch. But as we learn with these here, the double bond takes priority. Therefore, in our cyclic alkanes or alkenes and alkynes, carbon 1 and 2 is going to have the double bond in there. All right? And then after the multiple bond is numbered, the branches get the lowest numbers possible. And of course, list the branches in alphabetical order, just like we've done before. So we have a bunch of different ones right here. I'm going to do a cyclic and then a straight chain and let you guys kind of try some on your own as well. So as we notice here, so obviously we can tell we have a cyclic alkene, right? So we have a closed ring structure and it is an alkene because we see our double bond right here. Now, when we are numbering, there's going to be two different ways. So we see the double bond right here, so this needs to contain carbon 1 and 2. So we can number it this way. So we go 1, 2, 3, 4, and 5. So our multiple bond gets carbon 1 and 2, and that's the priority. However, we will notice that our branch is on carbon 5. Now, just like before, we got to try to get our branches in lowest numbers possible. So if we erase, not highlight. So if we erase what we've done here so far and try the other way of going 1, 2, 3, 4, 5, we'll notice now our branches start on carbon 3. Now 3 is lower than 5, therefore this is going to be the way we have to number this cyclic alkene. All right. Now as for our branches, we have methyl and we have methyl. So when we're putting all this together, of course we know our parent as well. So we have parent, we got cyclo, in this case right here, pentene. All right. So our name, we need to put in our branches first. So from our cyclic compound, we can tell we have 3, 3 dimethyl, and that's our branches. Now for our parent, normally we did have, like with a straight chain, we have to indicate where carbon 1 and carbon 2 is. However, in our cyclics are always 1 and 2, so we can just write cyclopentene, and that'll be the name. So 3,3-dimethyl cyclopentene. All right. So of course, there is another cyclic compound down here. I'm going to let you guys try that now in a second, but I just want to go over how to name our longest or our straight chained alkenes. All right. Now, just like our alkanes, we need to find our longest continuous carbon chain that contains, in this case right here, the multiple bond. So we can tell just by looking at our longest continuous carbon chain is going to be right across the middle right here. All right. So it contains all these carbons. We got 1, 2, 3, 4, 5 carbons in total. All right. So we know we should see pent. Now I'm going to leave this space blank. So we're going to see a pent blank ene. All right. Now I'm leaving that position blank just because what goes in between our root and our suffix is going to depend how I label these carbons. Now we know that our longest continuous carbon chain has to contain the multiple bond, and carbon 1 is the end closest to the multiple bond. Therefore, if we start from our left, it'll be carbon 1, 2, 3. So our multiple bond starts on carbon 3 if we go this way, 1, 2, 3. Now, is that lowest possible? Who knows? So I'm just going to erase what I have right here and draw the other way and see if I get lower numbers. So if I start on this end, I get 1, 2, 3, 4, 5. We'll notice that now the double bond starts on carbon 2. So that is definitely lower. So our parent chain is going to be pent2ene. Now what we have sticking up at the top here, right, this one is a methyl. So that's everything labeled. Now it's a matter of putting everything together. So just remember, branches get labeled first. So what we have right here is 4-methyl. All right. Now, our longest continuous carbon chain, we have pent 2-ene. And that is the name of that straight chained alkane. All right. Now, what would be very handy is to just kind of pause this for a second, try the other two, and I'm just going to put the names down very shortly. All right, so our next one right here, if you pause it and try it on your own, so of course we need to find our longest continuous carbon chain. So we can tell that we have a cyclohexane here, or sorry, cyclohexene. Now just remember, carbon 1 and 2 is always going to be on our multiple bond. So it's going to go 1, 2, or we are going to go the red route. I'm going to put here and go 1 and 2. Now, when you're given this position, so the multiple bond needs to contain carbon 1 and 2, we have to look at in this position, right, or in this case right here, we got to try to get our branches on lowest numbers possible as well, right? So if we go our red route, our first branch is on carbon 2. If we go our green route, our first branch is on carbon 1. Therefore, that rule of trying to get our branches on lowest numbers possible, getting a branch off carbon 1 is more important. Therefore, we're going to follow the green route, go 1, 2, and then we are going to go 3, 4, 5, and 6. So when we look at our branches, we have a bunch of methyls, and remember this one here, 2 carbons in a row, ethyl, these are methyl, and this is methyl. So when we're putting everything together, we know that we have a cycloalkene here, we have ethyl branch, we have methyl, so we are going to have to put them in alphabetical order. So on carbon 4 right here, we got 4 ethyl. Then we have branches off carbon 1, 5, 5, trimethyl. And then our longest continuous carbon chain, we got cyclohexene. Now remember, for cyclic compounds, we do not need to put the position of the multiple bond in between them because it's in carbon 1 and 2 to begin with. For our straight chain, we do need to include it. So in this case right here, carbon 1, carbon 2, carbon 3, and carbon 4 has to go across the middle. That is our longest continuous carbon chain. All right, so just right here throughout the middle. And the reason I'm starting on this end for carbon 1 is that we get our double bond on carbon 1, which is the lowest number possible. Right, and we have 2 branches right here. These are methyls. So the name for this one right here, we have on carbon 2 and 3, so we got 2, 3 dimethyl bute for 4 carbons. On carbon 1, we have our double bond. So 2,3 dimethyl bute-1-ene, and that is the name for that one. So if you look at the next page, there are more examples there on how to get them and drawing them as well. So now this is where it's up to you to either A, pause the video, or B, you can just close this right now, look at my answer key online and see if you get them, but I am just going to fill these out and put up the answers now in a second. All right, so pause the video and working. All right, and these are all the things filled in. So our first big one right here, we got 5-methyl het3-ine. So we had to start labeling over here on the left to get our multiple bond close to carbon 3. Our next one over here, we will notice I labeled this as carbon 1 for the same reasons before. We have our multiple bond has carbon 1 and 2, but we have a branch off carbon 1. That is the lowest number possible, so that's why it's 1,6-dimethyl cyclohexene. We have our next one right here. I had to start labeling here to get our longest carbon chain. We will notice that it has to go across and up and around this way to get 8 carbons in a row. And we end up getting 6,6-dimethyl oct3-ine, and we have our 1,6,6-trimethyl cyclohexene here as well down at the bottom. Now for our drawing, same thing, we always start with the N, start drawing them and go for it. So please pause the video, draw them, because I will put all the answers up in 3 seconds. 3, 2, 1. Oh crap, I didn't. Hold on. 3, 2, 1. And boom, here are the answers. Now, as you can tell, I decided to do all of them in different shapes. So I have right here just line diagram. This is a structural. This is the condensed structure right here on the last one. And this is the expanded molecular or expanded empirical formula. So what we have right here is inside this bracket, those are the branches, right? So actually, no, I forgot to draw. It's not butane, that's propine. Sorry. So this is CH2, and then we got CH3 at the end. So this. Oh, crap. I completely messed this one up. All right, sorry. I'm just going to erase this really quick and redraw in this condensed thing. So at the end, we got CH. Then we're going to get C. And then we get C with CH3, 2, and then CH3. So this is how this one looks. So how this looks as well. So if you did draw this out structurally, you'll see why this one only has no hydrogen. This bracket represents the two methyl groups. So if you look back on how we actually represent organic molecules, the brackets represent those substituents. And sorry about having that mistake there. And then of course our other ones are 2,3-dimethylpentene. And then even on the next page, we have our last two right here. So our 3-methylcyclohexene looks like this, and our 2,3-dimethyl cyclopentine looks like this with our triple bond. All right. Now we have right here, so this is an old diploma example that kind of has the whole idea about testing for our unsaturation, because we see our double bond right here. So I'll let you guys kind of read this on your own, answer the question, and then you need a chance to pause this video, read it, answer on your own, and I'll put the answer up now in 3, 2, 1, and boom, there's the answer, D. So you can tell the fumaric acid here has that double bond, so it is unsaturated, so that will cause the bromine solution to rapidly become colorless, and of course it is classified as unsaturated. Alright, so that is this, so please continue work in your workbooks, and of course if you have any questions, do not be afraid to email me, message me through Google Classroom, or we will find another way to communicate. Thank you very much, and see you guys for your next lesson.